give it that 1 minute. Okay, I think the big clock says 1:15. Let's get started. First of all, are there any questions about anything, technical or logistical? Okay, you should have successfully turned in your second daily problem as of today, so hopefully you figured that mechanism out. Any questions about that? Okay, two other logistical things I'd like to discuss before we get into the subject. First, we use Piazza in here as a discussion board. It appears that there is going to be some kind of Piazza apocalypse in like the next 48 hours where they're suddenly going to start showing you ads or requests for money or something like this. I don't know how gruesome this is. If this is gruesome enough that I should be switching to Blackboard, let me know. But for the moment, I'm assuming we can carry on. Okay? So if there's, let me know if something bad happens that I should know about. Second thing I'd like to try is, I've been talking with this mask this lately. The university got me a newfangled sort of clear mask, and I want you to take a look and tell me if this is an improvement. Okay, let me try this. And I think this is what I wanted here. Let me try this, hold on. Okay, do people feel that this here you have, okay, again, what?
It's a major improvement.
Major improvement? Okay, most people say if you cover more of the face, it's a major improvement. But actually, let's just take a vote here. There's three categories. One is big improvement. One is about the same. One is it makes things worse. Okay? Who here thinks it's an improvement? Who here thinks it's about the same? And who thinks it's worse? Okay, we're going to try this. Now, my last class when I tried putting this on, the students had concerns, my God, is this going to hurt you? Okay? And the mask is less comfortable than the other one, but let's carry on with this for a while and see if we'll try this from now on. And, okay, the other question, logistical thing, just to remind you, homework 1, you're now, probably after this class, you're starting to know enough that you guys can start thinking about homework 1. Not all of it, but part of it. So it may be something to start taking a look at. Okay, any questions? Okay, question? No. Okay, so let's go back and do the problem of the day. I believe, and you guys correct me if I'm wrong, this is the problem of the day. Okay, it has to do with looking at pairs of functions and trying to decide if there is a big O relationship or not. Okay? And let's try to think about how we think about these. Okay? And the real question, so we're interested in how is it, let me see if I can do this. No, okay, hold on. How is it that f of n, oh, terrible. Okay, hold on. That may be, that's more, okay, bad. Okay, how is it that f of n, let's try this again. Okay, something bad is going on. F of n compares to g of n. That was what the question was. And let's go to the problem of the day and see this. How does it compare to g of n? I should put a question mark here. Okay? So look at the first one. The first one we want to know, we have a function that is n squared plus little functions, and a function here that is n plus littler functions. Okay, and in case you haven't figured it out, when I'm trying to do these reasonings, we will prove it probably more directly later in the class, but the bigger term, the bigger polynomial term always beats up on the lower polynomial term. So if I think about this, this is really reducing to whether n squared, how is it that n squared compares to n? That's really what the question is, okay? And it should be clear to me, when I look at it like this, okay, on an intuitive level, it's clear to me that this is bigger than this, okay? Now, the big O is an upper bound, right? The big O asks if there's a greater than or equal to relationship. And that's not going to be the case here. The omega asks if there's a less than or equal to relationship. And that's going to be the case here. And the omega says whether or not it's equal. And if it's less than but not bigger, then it's not equal, okay? So for my way of thinking about this, because I understand this and I'm comfortable working with this notation, I know that the answer is the omega relationship. Any questions about that? Now, to be honest, the way you should look at it is where is the break-even point? Because remember, when you're thinking about the big O, you should always go back to the definitions, especially if you're confused. And so suppose it was n squared compared to 6n. Okay? What I need to know is what is a constant that I can multiply c times 6n by, such that if I'm trying to prove the omega relationship, such that this is always less than or equal to n squared. Well, if I want to figure out what that is, maybe I will cancel at the term, okay? And it now says to me, is there a value such that n is less than 6 times n, 6 times c? Well, if I set c equals to 1, then for all n greater than 6, this is going to be true. Does everybody kind of see that? So if you want to work this out more formally, remember you had to specify what was the constant and what was the n naught. Okay? Such that when you get for a large enough n, this side, in this case the right side, is always being beaten up by the left side. Okay? Now, part of it is that once I understand enough about analyzing algorithms, okay, working with the big O, I see this in my head instantly. But does everybody see that if you go back to the definition, the real way you would prove it was by giving what the n naught, proposing a pair of an n naught, meaning a value such that for all n bigger than this, and a c such that, one function is always above or below the other function. Any questions about that? Yes?
Can you explain again why we need a C value instead of just the value?
Why do I need a c value? Okay, so the easiest explanation for that is I want to prove that the big O holds, and the big O definition said, what does it mean for f of n to be bigger than c of n? It says it means that if f of n is big O of c of n, g of n, if and only if, okay, for all n greater than n naught, okay, f1 of n, okay, is, if this is, big O is an upper bound, this is what the definition is, okay? Remember, we started with the definition. So when you said, why do I need the definition? Why do I need the C? It's because there is this is what the definition is. If you want to say, does it satisfy the definition The definition is in terms of two constants. One for all n bigger than some threshold, so we know we don't worry about the small values. It's provably true that f of n is less than c times g of n for some c. Okay? So why do we need this? If we believe the big O is defined by this, if you want to prove to me does the big hold, you got to go to what the specs on the definition are. Does that answer your question or not? That seems fuzzy. Now, what you may now be arguing about is why do they use this definition? Okay? And why, again, the idea of big O, as we'll talk about dominance, is a way to break functions into kind of tiers based on roughly how do they grow as a function of n. Okay? This is a useful thing to do. It's useful to know that 2 times n squared is not that much different than n squared. Okay? Whereas n squared is much bigger than n to the 1.999. Okay? So that's why we care about this big O idea, because it's important to break functions into categories so we can do rough analyses of time that will tell us which category does this algorithm belong in. Okay? And the formalities of how they define these categories are based on this notation. Any questions about that? Yes?
How would you want us to disprove that it's now big O or it's not O?
How would I want you to prove what exactly?
Disprove it n squared is greater than n, so we want to prove it.
Okay, so okay, so how would how formal is it? Again, I don't find. Okay, so let's be precise. Okay, so it's important to be able to talk correctly about the big O notation because we're going to be using it as a notation. The properties of it are not so magically concerned. I don't really care about it provided you understand what the idea that there are upper bounds and lower bounds and things like this. Now, how did I make this more precise? Well, I guess my argument was that if I have the function here was n squared, and here was 6n, okay, that I could choose a particular c. Here I chose c equals 1. And then I could look to see where does the left side equal the right side. And if I argue based on a simplification, like converting the n squared to 6n, maybe you can't tell how n squared compares to 6n. But you can tell how n compares to not to 1. That's why canceling by the n here, okay, made it simpler. Okay, and then so simple I could then solve for what was the break-even point, where the function on the left was less than the function on the right. Okay? I don't know if that gives you an answer, but that's at the moment my answer for you. Any questions? Yes? Where does the n greater than, recognize that the screen is not calibrated, and when I try to write on the right of the screen, things move further from where I want them to be. So here's my attempt to write right next to the, on the dot. See how when I'm trying to write on the dot, it's going someplace to the right of it? So what is, how do I get this thing off? Good. So what is this saying? I want a constant to multiply the thing on the right by. The thing on the right here is 6n. Okay? Such that n squared was always greater than it. Okay? And so you specify, there's two unknowns here. There is a c, and there is the bound where it's after which, and not where after beyond which, for what value is n larger than. This is in fact really is an upper bound. If you choose n equals 4, you can use n equals 4 as far. Again, n, what that n is a function of c. Suppose I put C equals, instead of 1, I decided C should be equal to 100. Okay? Now it is harder for the thing on the left, n squared, to be bigger than the thing on the right, which is now 600n. Right? So depending upon what C is, that sets the exact value of n naught, the cutoff, such that it really is an upper bound. Okay? Any questions? Once you understand the definitions, this is not very interesting. Okay? Because we're going to be using it as a language for comparing functions, and I'm not going to really care about these details very much. But it's important to understand what the definition is. Any questions? Let's look at the second problem. How does n to the square root times square root of n compare to n squared? Right? This looks frightening except for one thing. What is the square root n function? Does anyone know? Okay, yeah? N to the 1/2. So what this is really saying is, how does n to the 3/2 compare to, to n squared? Right? And now what do we know? We know that this is now an upper bound, right? How does this compare? Well, let's look at the thing. Well, one thing I can do is I can cancel both sides. And if I divide both sides by n to the 3/2, this is this is going to be 1. And on the other side is going to be n to the 1/2. This side is going to keep growing as n gets bigger. This side is not going to keep going. Right? So when you ask me, this is now an upper bound. G of n is an upper bound on f of n. Does everybody kind of see that? And if so, what does that mean? That would be the big O. Any questions about that? Do people kind of agree with that? Good. Now let's take a look at the last one. And the last one is a little bit tricky. Again, little on, when I talk about dominance, I'm going to note that I can delete the smaller terms. The real question here is, it's a little bit funny. How is it that n squared compares to n to the 4th? Okay? Let's just say that those, I'll tell you, are the bigger functions on which half. Which number is bigger, n squared or n to the 4th? 2 to the n or n to the 4th? Which is bigger? Okay, who here thinks 2 to the n is bigger? Who here thinks n 4th is bigger? Who here really thinks they know why 2 to the n is bigger? Okay, why is 2 to the n bigger? Someone loud. Yeah? Okay, I unfortunately don't have that kind of hearing, so you need loud. Okay, so one talking point is to say that this is an exponential function and this is a polynomial function. And if you believe, like I will tell you, that polynomials are always beaten by exponentials, then that's something you can remember. But do you feel that in your bones? Why is it that there's a difference? Okay? Let me try to convince you that this is in fact bigger than that. Does anybody know, and if you don't know it now, you'll know it later in the class. Uh-oh, God darn it. What is 2 to the log n? Does anybody know what 2 to the log n is? Okay, somebody, yes? That's n. Does everybody see that? So does everybody believe that 2 to the log n, whole thing, raised to the 4th, does everybody believe that that is n to the 4th? Right? Now, notice that I could write n as being equal to, and when you multiply two things that are logs, 2 to the log n times 2 to the log n, you add the exponents. Is that right? Okay. So I claim that log n to the fourth is really 2 to the 4 times log n. Does everybody kind of believe? Let's think about this for a second. Is this what n to the fourth is going to be? Okay, I hate this screen for the record. But any questions about that? Okay, if you believe that, what do I know? N is equal to n minus, okay, take it back. N minus 4 log n plus log n. Does everybody agree with that? Plus 4 log n, excuse me. Actually, let me do it on the board, since the math I have a harder time. Does everybody agree that n is equal to n minus 4 log n plus 4 log n? Does everybody agree with that? That's supposed to be trivial, right? So what does that mean? That means that 4, what does it say on the other side? 2 to the n is equal to 2 to the n minus 4 log n plus 4 log n. Does everybody agree with that? Again, this seems pretty obvious. What's on the other side? The other side is n to the fourth, which is what? 2 to the 4 log n. Does everybody agree with that? We want to compare, let's say this is a question mark, which side is bigger? You wanted to know whether 2 to the n is bigger than 4 to the n to the fourth. Does everybody agree that's what the question is? N to the fourth is 2 to the log n times 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 2 to the log n, or 2 to the 4 log n. Right? On this side, this is 2 to the n. How does this compare to it? Well, note that we could divide if we took the log of both sides. Okay? Now, this side is going to be, what you call it? This, okay, what am I trying to say? This is 2 to the big thing times 2 to the 4 log n. This side is 2 to the 4 log n times 1, right? If I put the ratio of this to this, what would I get? What do I get if I have 2 to the n, okay, divided by 2 to the 4 log n? What do I get? I claim that what I'm going to get is 2 to the n minus 4 log n. Does everybody agree with that? When you divide something, you basically subtract the exponents. Okay? What does this mean? It means that this side is bigger than that. Actually, I think I've talked this through too much. But one way to think about it is 4 to the n, let me say it one more time. N to the fourth is 2 raised to the this, right? 2 to the n is 2 to the this, right? Does everybody agree that if I divided both sides by this side would get to be 1, and this side would get to be n minus 4 log n, right? This side will keep growing with n. If I divide both sides by 2 to the 4 log n, this would be 1. This would go away. This side would still be bigger. This side is going to keep growing. This side is not going to keep growing. That is really the argument that the exponential is growing faster than the polynomial. Basically, n becomes 2 to the log n, and 2 to the log n can't compete with 2 to the n. Okay? Any questions? Yes? So you're saying, well, wait, don't you really just want to talk about limits? Well, I'm thinking in terms, the answer is yes. Limits are the right way to think about it. When we talk about dominance in a few minutes, we'll be talking about limits. But another way to think about it is that if we took the limit of 2 to the, let's say, if we took the limit of n to the 4th over 2 to the n, what would the limit be of n to the 4th over 2 to the n as n gets bigger and bigger? What would the limit be? 0. This is small, this is big. The ratio of small over big is going to go to 0, right? So that's a similar argument to say this function is growing faster than this one because the limit is going to 0. That's another way to look at it, and that's how we'll define dominance in a minute. Any questions? Okay. So what is the point here? The point should be that, in fact, this clearly grows much faster than the other one, and that we're in a situation of an omega. Any question? Of a theta, I mean. No, an omega. Any questions? Okay. Any questions about this problem? Okay. Yes? Why am I saying using the Greek letters of big of O of omega? What do we call it? Blah, blah, blah. Theta and omega. Why am I using that? That's because it's used by other people before me, and I want to be able to talk to them. Okay, so this is a standard notation. Any questions? Okay. Any questions about this now? Okay, let me try to clear the slide and move on. Okay, let me see if I can do this here. Boom. No. Okay. So let's go a little bit more just to make sure we understand how the big O notation works. Some consequences of it. One thing that's clear is that if you multiply a constant, a function f of n, by some constant that's not 0, some constant greater than 0, okay, it doesn't change the big O-ness. N squared is the same as 6 billion n squared. It's the same as 1 over 6 billion n squared. Why is that? Because if you want to compare some constant c times f of n to f of n, well, there's always some other thing you can multiply f of n by to make it bigger than c of f of n for any c. If you multiply it by c times 1, it will be bigger, right? So multiplying functions by a constant doesn't change the asymptotics. That's the first thing to note. And I think that's clear. Any questions? Now, multiplying two functions, okay, by each other does change the asymptotics, okay? If I multiply, let's say, n times n, okay, the function at the end is going to be order n squared, okay? So multiplying functions changes the asymptotics over it. Multiplying a function by a constant doesn't change the asymptotics. And if you think back to why we're doing this whole big O thing in the first place, we wanted to use it to count up how algorithms run, right? Now, what is the time complexity of something like selection sort? You guys have seen, or bubble sort. I think you guys were brought up on bubble sort, right? What is the big O time complexity in the worst case of bubble sort? Yeah? O of n squared. Why is it n squared? It is n squared because you have an outer loop that goes 4i goes from 1 to n, and an inner loop that goes around basically up to n times, right? And so n times up to n is up to n squared, okay? So whenever you have two nested loops, both of which go around n times, you have something that runs in order n squared. If you have something that's a nested loop and then followed by another nested loop, this goes around order n times, this goes around order n times, the total time would be n plus n. If you have a loop and a loop inside of it, every time this goes around, I pay another n here. That's n times n. That's why it's quadratic. Any questions? Okay. Any questions about what I'm saying here? Okay. So why are we going to use the big O here? In general, we're not going to be proving lots of complicated things about big O note, about comparing one function to another. We're going to be wanting to take algorithms and reason about how many steps they take in the worst case, okay? And so in general, the analysis that we're going to be doing is you're going to have to, there has to be an algorithm that is specified clearly enough that you can roughly count the steps on it in. Usually for you at the beginning, this should be an algorithm that is written on a piece of paper. If you see an algorithm on a piece of paper, you can reason about it. Sometimes I'll skip a step and I'll say, oh, this algorithm is n log n. And why am I able to say that? Because on the back of my retina is a printed version of the algorithm. And I am reasoning about that printed version. Okay? Recognize that if you're confused about where the analysis of an algorithm comes from, the first thing to do is to make sure your algorithm is written down and you can reason about it. Again, so let's take a look at a printed algorithm and try to reason about it. Okay? This is an algorithm called selection sort. Okay, what was selection sort? How did selection sort work? Well, suppose we had a bunch of numbers, let's say 3, 7, 1, 6, 2. What did selection sort do? It would go through all the numbers and find the smallest one, which happened to be here, and then swap it with the first number. Then it would move in, okay, by 1, and now look at the subarray from the second to the last number and find what was the smallest number in here. Bop, 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 bop. It was a 2. Swap the 2 and what was there? Then it was going to look at the smaller subarray. What's the smallest number that's there? It's the 3. Swap the 3 with itself. Now it's a 6 and a 7. Swap the 6 with this. Now look and find the smallest here. 6 is the smallest. Swap 6 with itself. 7 is the smallest. Swap 7 with itself. That is what selection sort is. It always finds the next smallest number. Okay? And as you can see, I did this by, I said I'm going to have an outer loop that's going to go around n times. And then the inner loop goes from I plus 1, because the first I numbers are assumed to be sorted. This is what's going to go look inside from the I plus first to the nth number to find what's the smallest one of the bunch. Okay? And then afterwards it'll do a swap and move on here. What is the number of steps? Any questions about selection sort? How it works? You guys have probably seen this before. Okay? What is the running time of selection sort? Big O-wise, looking at this code, yeah? You say it's n squared. Why is it n squared? Okay, so you're giving me something n over n squared over 2, whatever that means. Let's think what we're talking about. First, if we're thinking about big O, does big O mean an upper bound or a lower bound? Upper bound. Does this thing, can we show that n squared is an upper bound on the number of steps to get done? Well, this outer loop goes around how many times? It goes around n times. Does everybody see that? Maybe it's even n, I think it's n. Could be n plus 1, but n. How many times does the inner loop go around? Okay. I claim the inner loop goes around less than or equal to n. Does everybody see that when I equals 0, this goes around n times? When I equals n minus 1, it goes around once, right? Does everybody agree that 10 times, okay, at most n is at most n squared, right? At most n squared means it's an upper bound. N squared is an upper bound, right? So this is the argument that would prove that selection sort is order n squared. Okay? Any questions? Now, the simplest way to analyze an algorithm is to think about what's the worst case at every single step or loop and count that. Now, for some algorithms, as we'll see, that's being too pessimistic. And in fact, the algorithm runs better than that. Okay, even in the worst case. But a simple way to deal with the worst case algorithm is to assume the worst case at every loop, and that gives a big O running time on the worst case. O of n squared. Any questions about that? Now, if we want to know the worst case running time, if I told you that selection sort was big O of n cubed, would I be telling you the truth or not? The answer is yes, this selection sort is big O of n cubed. Why is it? N cubed is bigger than n squared. If it runs an n squared, it is. If I've proven it always takes at most n squared time. It certainly takes at most n cubed time, right? Saying that, if I tell you that, if you know that, let's say I have, you know that he has $200, okay? If you told him that, if you said he has less than or equal to $1 billion, are you telling him the truth? Yes, but it's not very interesting unless the bound is close. How do we make this bound interesting? To make it interesting, we have to actually argue that the worst case running time of this actually is n squared, right? We don't really believe that it's big O of n cubed. Is there an argument that it is n squared? And that gets back to what this guy is saying. How much does this loop go around actually? It goes basically around, first time it goes around n, then n minus 1, then n minus 2, down to 1. Does everybody agree? That's the actual number of steps taken in here. What is the sum of I as it goes from 1 to n? Does anybody know that from your combinatorics class or anything like that? What is that? Yeah? You're telling me this is equal to n times n plus 1 over 2. Maybe you're right. What do I know about that? That's basically going to be n squared. If I wrote that more carefully, I like it on the board. Because it was n times n plus 1 over 2, does everybody agree that that is less than or equal to n squared? And does everybody agree that this is less than or equal to n squared over 2? Does everybody agree with that? If so, what does that mean? This quantity is not big O of n squared. It is big theta of n squared. Does everybody see this? I have both an upper bound, which we argued about, and a lower bound. Okay? By saying that, it means that this algorithm really does take n squared on some example. Okay? And therefore, that's my justification for not saying that it's big O of n cubed. That's my justification for saying that the running time of selection sort is really theta of n. It's not that n squared. Okay? Any questions about that? To make sure that your upper bound is good, you have to give me a lower bound argument, right? To argue to me that the algorithm really does take that much time. Any questions about that? Otherwise, you might end up with a very, very soft bound. It's okay to have a correct bound that's soft. It's better to have a correct bound that's right. Any questions? Okay. Sorry about this erasure deal. Okay, good. So what did I say? Basically, there's an argument that in fact, for at least half the elements, okay, it's going to take at least for half of the iterations, it's going to have to go through at least half the elements. That's another way of saying that this is going to have to take at least n squared over 4 steps. And if it takes at least n squared over 4 steps, that's what's going to be used to give me my omega bound. And if the omega bound and the big O bound match, it gives me a theta bound. Any questions? Good. And again, you can count it more carefully, but again, we prove a theta bound from that. Any questions? Yes?
If you have something with like a time complexity of n squared plus n, what exactly would the upper bound be?
Okay, so it's the n squared. You're saying, wait a second, if my running time is n squared plus n, my claim is, do you believe that n squared plus n is less than or equal to 2n squared? And do you believe that it's greater than or equal to n squared? I think you believe this. Do you believe that n squared plus n is bigger than n squared? Do you believe that n squared plus n is less than 2n squared? You don't believe it. Well, let's try to convince you of this. What if I take this and I subtract n squared from each side? What would I get? You're now comparing n to n squared. Do you believe n squared is bigger than n? Tell me I don't believe it yet. You're still skeptical. What if I divided both sides by n? Do you believe that n that goes to infinity is bigger than 1, stays where it is? Now I think you believe it, right? What do we know? If the function that you have here is between n and 2n squared, what do I know about this function? You know that it is theta of n squared, right? So adding these lower terms don't really matter very much. That's kind of the important point here. In a big O sense, it doesn't matter what those lower terms are. Okay? That's why I get cavalier and throw them away. Okay? Any questions? No, you're right. When I went back to the previous algorithm, I didn't count the cost of the swap. Why didn't I count the cost of the swap? Well, this loop goes around n times. I do one thing for the min, one thing for the swap, n things for the loop. And what's n plus 1 plus 1? N. Okay? If I'm doing this in a big O world. Any question? I live in the big O world because it makes my life simpler. I don't have to count exactly because I know what's important and what isn't. Any questions? Okay. Let's try to do this with insertion sort. What is insertion sort? Does everybody remember the insertion sort algorithm? If I had numbers, let me think what my numbers are. Let's say I have 1, 5, 1, 3, 4, 2. How did insertion sort work? It started out from the left and said 5 is perfectly sorted. Now let's sort the rest of it. How do I sort from here, from the second element? I go and I walk it through the elements that are in the sorted part. And that means that I've got to swap it here with the 5, right? And now 1, 5 is sorted. What about the third one? The third, is it less than 5? Yes. Is it less than 1? No. So I'm going to swap this. This is going to be a 3 and this is going to be a 5. What about the 4? I swap it here. 4, 5. 3, 4 is bigger than 3. I stop moving. I don't have to go any further, right? Because once I found the spot here, it's stuck. Now what about the last 2? Does it go ahead of the 5? Yes. Does it go ahead of the 4? Yes. Does it go ahead of the 3? Yes. Does it go ahead of the 1? No. It ends up right in there. Does everybody see that? So what is insertion sort doing? For each of the n elements in the array, it's going to basically start to check. This is going to be a counter that goes back and walks to the next element over to the left and checks to see if it is less than the previous element. If it is, it swaps it and it keeps walking. If it doesn't, it gives up. Okay? Any questions about what insertion sort is? Now, when you look at the code, let's try to analyze it. What is the running time of this algorithm? Okay? Well, we get very excited when we see a for loop, because for loops, we know how much they go around, right? This goes around n times. We have a while loop here. Okay, fair. The while loop. How many times does the while loop go through on each iteration? Is there any guarantee you can tell me? Does everybody see that that while loop is going to go through a different amount of times on every element? Right? So how can we reason about this? Okay, yes?
The worst case is if the insertion has to go all the way through to the...
You're saying that the worst case, it would have to, if it walked to, even if it walked to the end, it would always go through less than or equal to n times. Does everybody see that? And now, what do we know about insertion sort? It is n times less than or equal to n. That is less than or equal to n squared, right? That is a big O of n squared. Okay, God knows what to... Does everybody agree that n squared has to be an upper bound? Because it's n times less than or equal to n. Okay? But now, if we're talking about the worst case running time, does this always take n squared on every example? What's an example where this won't take n squared time? Yeah? When it's already sorted, it'll say, I'm in place, I'm in place, I'm in place. After n comparisons, you're done. But if you want to argue that insertion sort is in the worst case, really is theta of n squared, you've got to give me an example where it actually does that badly. Is there an example where insertion sort does that badly? Okay. Somebody in the back of the room or more in the back of the room? Is there an example of where insertion sort does badly? Okay. Yes. Reverse order, right? We almost had a proof that the insertion sort does not behave badly in the back of the room. But if we in fact have the things that are in reverse order, okay? If it's in reverse order, what is the argument? Okay? The argument is that every element is going to skip all the way to the left when we insert it. And so it's going to jump over 1, 2, 3, dot, 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 the sum of 1 to n things, which is n squared over 2. So there exist examples where insertion sort will take n squared over 2 time, meaning omega of n squared. Omega of n squared. We have a big O and a big omega. We've got a theta there. Any questions about that? Okay? Again, I kind of expect you to be able to now look at these algorithms. Look at the text of an algorithm and give some kind of a worst case analysis of it. Once you know how to do it, this is not a hard thing. Finding an algorithm that does the best worst case is good, okay? But reasoning for a particular piece of code, prove me that it doesn't take more than this many steps ever, and ideally then match it with somebody else, an example, and says here it does take that many steps, okay? Then you've got the upper and lower bound, meaning the theta bound. And you know what the worst case really is. Any questions? Okay, good. What I'd like to talk about here, maybe I'll cut over here because I think I'm running a little behind, is why we care about these big O classes, okay? Algorithms do, in practice, wildly different things on large N, depending upon whether they are log N or order N or N log N or N squared or 2 to the N. So this is now assuming you have a computer where it does, a billion, maybe it was a billion instructions per second. How long would it take to solve a problem of size N as a function if its complexity was N log N or N squared or something like that? When you look at a table like this, it's really kind of amazing. For a log N time algorithm, you're dealing with microseconds even if you've got a billion, N equals a billion. A log time algorithm like binary search never takes any time. A linear time thing, if you could solve a billion instructions, what is this? This is a billion, this is a billion. If you're doing a billion instructions a second, then you have a linear algorithm, it'll take 1 second. Right? So for even large N, linear time algorithms are just fine. N log N algorithms, like fast sorting algorithms, that would take about 30 seconds for a billion, but it's still not an impossible thing. If you have an N squared algorithm, Notice that on a billion, example of a billion, an n squared algorithm takes on the order of 30 years. Okay, that's as long as I've been here at Stony Brook, and your algorithm would still be running. Okay? For a 2 to the n exponential algorithm, by the time you get up to n equals 100, you're talking about not years, but billions and billions of years of computation. And when you're dealing with an n log n algorithm, an n factorial algorithm, by the time you get to 30, you're dealing with billions and billions of years of computation. So this is why, if you proved that if sorting was n squared, the world would look wildly different than we do now. I don't know if you have these Twilight Zone episodes where the world suddenly changes. Imagine you woke up in a world where there did not exist n log n sorting algorithms. The world would be wildly different. We couldn't process big pieces of data the way that we do. Because there's a difference between something taking seconds or something taking years. Okay? You'll be grateful you woke up in the world of today where we have n log n algorithms. Okay? Any questions? Okay? Fair enough. And these are basically the lessons that you should learn from a table like that. Okay? Quadratic algorithms are good if your choice was exponential. Quadratic algorithms are great if compared to something n cubed. Quadratic algorithms are terrible compared to n log n. Okay, any questions? So when we talk about these classes of algorithms, there's this notion of how does one class compare to another, and this gets into the thing about limits. We say that a function f of n dominates a function g of n if the limit of f of n over g of n goes to 0. Okay? Does everybody kind of get that idea? If f of n grows much faster than g of n, the limit of f of n, g of n over f of n would be 0. Okay? Any questions about that? Another thing, so we say that f of n dominates g of n. Another way to say that is that g of n is dominated by f of n. Does everybody kind of get that? If I dominate you, you're dominated by me, right? The little o notation says that g of n is dominated by f of n. Okay, occasionally you'll see the little o notation, which means that the thing on the left grows strictly slower than the thing on the right. Okay? So write that down for when you see a little o. Question? What?
Is that similar to omega?
It's similar to omega, but not allowing equality. Okay? So is n squared theta omega of n squared? The answer is yes, right? But n squared does not dominate n squared, right? The difference is with equality. It's like omega, but it forbids the idea of equality, right? If they're equal, nobody wins. Otherwise, one dominates the other. Any questions? So if you believe this limits definition, then you start to see better about how complexities work, how the big O works in things. Suppose I have a polynomial n to the a, comparing that to n to the b, where a is bigger than b. Well, if a is bigger than b, the limit of n to the b over n to the a is n to the b minus a, right? And if a is bigger than b, this goes to 1 over n to the a minus b. This goes to 0, right? This is why I'm always trying to lower the exponent of my function. If you have an algorithm that is n to the 1.999, and you compare it to a quadratic algorithm, n squared, this one, by our notion, beats the pants off of this algorithm, right? This function is much bigger than this, right? The limit of n to the 1.99 over n squared is 1 over n to the 0.0001. N to the 0.0001 will get to infinity. 1 will stay where it is. The limit here would be 0, right? So whenever you have a bigger exponent, okay, that means it's a bigger function. And if we're looking for worst case complexity, we seek the lowest function. Okay? Any questions? Likewise, you were asking me before, oh, what about something that was n squared plus n? How does that compare to something that is n squared? Okay. The limit, what's the limit of n squared over n squared plus n? What does the limit of that go to? 1. Okay, it doesn't go to 0. That's because they are about the same. Okay? What is the limit of n over n squared? It's dominated by it. Okay? So what does this mean? Adding a lower order term to a function doesn't change its big O complexity. Right? That's why I tended to ignore these extra terms, because they can't possibly have an effect on the which function dominates what. Any questions about that? Okay? Any questions? So what dominance relationships should you kind of know? Because they're going to come up over and over again. In this class, we will see algorithms pretty much with these complexities and not that many other ones. Okay, these are kind of bread and butter kind of complexities. Log n dominates 1. N dominates log n, because n is 2 to the log n. That's a really big dominant, right? N times log n is bigger than n, because the ratio of n over n log n is 1 over log n, right? N squared is much bigger than n log n. N cubed is bigger than n. 2 to the n is way bigger than n cubed. And n to the factorial is way bigger than 2 to the n. Any questions? You should recognize that, and when you're designing algorithms, you should be dreaming of the lower end of the spectrum. And you should be trying to design algorithms that are as far to the right as you can. And, this I think should be clear. Any questions? If you take, a sufficiently, maybe you take another more advanced algorithms course, you will discover that people have developed all kinds of strange algorithms with other complexities, okay? That are, but again, there's a hierarchy here. And if you want to look at these things, you should know that the log of n is much smaller than the log of n. Okay? The log of n divided by log n is smaller. Bottom line is that we're not going to get into, I think, algorithms with these kind of complexities. But understand that there's a world of functions out there that are organized by dominance, and any one of them may very well have an algorithm that runs in that time. Okay? Yes? What is this a to the n thing? Okay, there is an algorithm, there is a function called Ackermann's function that is an extremely fast-growing function. And there is something called the inverse Ackermann function. And that is something that's an extremely slow-growing function. And that's what this is. We'll actually see an algorithm that really runs this semester that really does run in alpha n times. So it's not constant, but it's really, 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 really fast. We're not going to analyze it that closely. We'll show that it's log n, and that's good enough for engineering work. Okay? But these things do come up in sufficiently advanced algorithm analysis. Any questions? Okay. Okay. What is the final topic I want to talk about today? This is a simpler topic than dominance, but it's a very, 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 very important that everybody kind of come to understand this, or else make sure they have a feeling for logarithms. Because if you don't really know where logarithms come from, you're going to be baffled all semester. Okay? What is a logarithm? A logarithm is a, the inverse exponential function. That's what it really is, okay? So when we have an expression that says if we take b, let me try a different color to prove that I've got that power. If I have an expression like b to the x is equal to y, what we're saying here is x is the exponent, that if you raise b to it, you get y. By definition, that is the log, okay? So saying that x is equal to the log base b of y, that is exactly saying that b to the x is equal to y. These are two equivalent statements by definition. Okay? And you have to see that. The logarithm, which is x here, the log base b of x, is the power of y, base b of y, is the power that you take b and raise it to get y. Okay? Any questions? Okay? You have to internalize that definition. Okay, the log is the, the exponent. Okay, any questions? Now, the reason why we are interested in logarithms and algorithms is that a lot of things, algorithms really reduce to repeatedly doubling or halving something. Okay? How many times should I double x? How many times could I double 2 till I got it equal to n? Okay? Suppose I start with 1, 2, 3, 4, well, think about it. 1, 2, 4, 8, 16, 32, 64, 128, ... How many doublings does it take to start from 1 and get to n? How many doublings? Yeah? Log base 2 of n. This has to be in your bones and in your heart. Okay? Or, how many times do we take n and halve it until we get down to 1? N over 2, n over 4, n over 8, n over 16, ... Well, we want to know how many times do we double the denominator until we get to n. What is the power of x that we have to raise 2 to get it equal to n? What is that power? Log base 2 of n. Does everybody get that? Some of you are going to spend all semester seeing I put up a log on here. Where did that log come from? I know about n and I know about n squared and I can divide. It's about whenever there are things with repeated doublings or halvings, That is really the source of these logs. They don't pop out algebraically in the way some other things do. Okay? But that's an important thing to understand. Any questions? Okay? Fair enough. Now, some of you have heard of binary search. Okay? What is binary search? You know, you have this idea that you have a table of n sorted things. How do you find if Skena's in the phone book? I don't know if you guys know about phone books anymore because you're digital. But you look in the middle and you compare. Is, you know, the key in the middle before or after the number you're looking for? If it's before the number you're looking for, the item's in the first half. If not, it's the items in the second half. And then you recur on the appropriate half containing your key. That's binary search. Has everybody heard of binary search before? What is the running time of binary search? Somebody yelled. Does anybody know? What is the running time? Log n. And why is it log n? It's because log n is the number of times you can have something until it goes from n to 1, right? That's the name of this quantity. So the answer is it's got to be log n. Okay? Any questions about that? When you have a binary tree, what's the height of a tree? You guys know about trees. There's a tree. There's a tree of level 2. There's a complete tree of level 3. Level 4. How high do I have to make a tree until the last level contains n things to it? What's the height of a tree, a complete balanced tree that has n leaves? What is the height of that? I heard a weak log n. Why is it log n? Yeah? Because log of 2 to the n is n, log of 2 to the x is n. Another way I think about it is the log is counting how many doublings it takes, right? To get from 1 to n. You started out with 1 level leaf. Then it would have been 2. Then it would have been 4. Then it would have been 8, right? How long do you have to double this till it gets down to n? How many? Log n. Okay? That's because that's what log n does. Okay? We're going to be interested whenever we have processes of repeated doublings or repeated, divisions. That's where a log comes in. Any questions about that? Okay, good. Suppose you are designing a computer and you want to know what your bit length is. If you want to represent a certain length of number, right? Integers, binary notation. If I have a 4-bit computer, bunk, 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 what is the biggest number I can represent in a 4-bit computer? Does anybody know? What is the biggest number you can represent with 4 bits in binary? Somebody. What? With 4 bits? Well, you could have it be 1, 1, 1, 1. What is that in binary? Okay, I'm hearing different things, but not anything that sounds right to me. Someone with a hand. Yeah? 2 to the 4th minus 1. You're saying that this is 2 to the 4th minus 1. Why is that? Well, this is the 1's bit, the 2's bit, the 4's bit, and the 8's bit, right? So that's 1. 8 plus 4, which is 12, 14, 15. This is 16 minus 1 equals 15. Does everybody see that? So, if I have a number, I want to represent the number n in binary. How many bits do I need in order to represent the number n? Yeah? You're saying that in fact, oh, okay, you're telling me 2 to the power log n. How many bits do I need? We agree that we're going to represent it. How many bits do I need to represent an n-bit number? I mean, a number that goes up to n. Okay, to represent 15, I could get away with 4 bits, right? What if I have a number, I want to represent the number n in a computer? How many bits do I need? Somebody, yes? I need log of n, maybe plus 1. Why is it going to be log n-ish? What's the biggest number I could represent if you give me an extra bit here? Does everybody see I'm going to add the number 16? I'm going to double my range of numbers, right? The size of the numbers you can represent doubles with every new bit you add, right? So what is the number of bits I need to get to n? I need to know how many doublings does it take till I get up to n. Does everybody kind of see that? Okay? This is important that you come to feel this in your, in your thing. By definition, logs are going to arise whenever, you're going to have doublings. Okay, or change it, doublings or halvings. Any questions? Let me do one last thing about, okay, hold on. One last thing today about logarithms, and then we'll continue next class. One other property of logarithms that is kind of important, or especially used to be really important, okay, was what is the log of x times y? Remember, you've got a base A. What was the log of x times y? Does everybody remember you had this in high school at some point? What was the log of x times y? It was the log of x plus the log of y. Right? Actually, you've done this before. What is the log? Show me that you do this. What is the log of n squared? Does anyone remember what the log of n squared is? Okay. Yeah? 2 log n. Now, why is it 2 log n? You're telling me this is equal to 2 log n. Why is that 2 log n? Make that an O, log. Why is it 2 log n? One way is to look at this. What's the log of n times n? That's the log of n times the log plus the log of n, right? If you believe this expression, okay, it would give you that this is equal to 2 log n, right? What's another question? What is the log of 2 to the n squared? It is going to be, what is the x? Such that 2 to the x is equal to n squared. What is that? That's by definition, right? What is that x going to be? What power do you have to raise 2 to the 2 in order to get log n? To get n squared? Well, we know 2 times log n gives me n. 2 times log n times 2 to the times log n is going to